Hi everyone, thanks for giving me an opportunity to present at WIN conference. I am going to discuss QED radiative corrections to charge current elastic neutrino scattering on nucleons. This work is motivated by ambitious goals of the future US-based neutrino physics experiment DUNE, with main goals to discover or rule out CP violating phase in the lepton sector and to measure oscillation parameters precisely. As in all neutrino oscillation experiments, the information is extracted from the number of neutrino-induced events, which is given by an integral over the neutrino energy of flux times the cross-section and times the response of the detector. Performing measurements at different distances along the neutrino beam direction, we can count how many neutrinos appear or disappear. Tuning the production target to anti-neutrino mode, we can extract also CP violating phase. A near detector is planned at Fermilab, and far detector is under construction at South Dakota. To achieve a percent level in such experiments, one has to understand neutrino cross-sections precisely. This is true also for other experiments in neutrino physics. In DUNE, cross-sections with muon component can be measured at near detector since the beam consists mainly from muon neutrinos, while electron flavor cross-sections, which is a signal process, or muon over electron cross-section ratios should be taken from the theory. To achieve a percent level of precision, we should think about radiative corrections, and I'm going to briefly explain why. Let us take a look on how neutrinos interact with target of any origin. After scattering, either the target recoils or new particles are produced. Any charged particle can radiate energetic real photons or exchange virtual photons with other charged particles. All these radiative corrections are suppressed by small electromagnetic coupling constant and unevenly off per mil level. However, for oscillation experiments performed at GeV energies, we have a scale separation between lepton masses and energy of the experiment. Radiative corrections can enter with enhancement by logarithmic terms or even double logarithms when we place experimental cuts on kinematics of radiated photons. That is why the net effect can reach 10–20% in case of electron flavor and is slightly smaller for the muon flavor. Dependence on the mass can introduce a significant flavor dependence, which is important in the connection between electron and muon cross-sections. These effects are not part of event generators or experimental analysis, but should be correctly accounted for. Many neutrino-induced processes are important at GeV energies. In kinematics of modern experiments, quasi-elastic process, resonance production, and deep inelastic scattering contribute. Cross-sections divided by the neutrino energy are presented on this plot. Also, the range of neutrino fluxes is shown. I will focus on quasi-elastic process, which is a signal channel and a tool for the neutrino energy reconstruction. I'm going to concentrate on the elementary interaction with nucleons. At tree level, the scattering amplitude is given by product of currents. Lepton current is known analytically. Nucleon current is a matrix element of this quark operator. It is determined by 4 form factors: 2 vector and 2 axial. Assuming isospin symmetry, vector form factors are expressed in terms of electromagnetic form factors, which we take from electron scattering and spectroscopy. Axial form factor is the main source of uncertainty in neutrino-neutron scattering. It is mainly extracted from deuterium bubble chamber data. I will concentrate on radiative corrections to this process. I would like to mention that besides neutrino-neutron scattering, we always consider anti-neutrino proton scattering as well. As we know, processes with electrons in final state, such as neutrino-electron scattering, are subject to percent level corrections due to logarithmic enhancement. In experiments with nuclei, different setups are possible. One can reject events with photons of energy above delta E, and such restrictions of the phase space result in double logarithmic enhancement, well-known Sudakov double logarithms. Measurements with magnetic field can disentangle the collinear radiation from recoil lepton in principle. But typically, we measure both photon and final electron. That's why our observables are subject to collinear logarithms. Double logarithmic terms can enhance the correction up to 10–20% and are crucial for percent level measurements. This is our motivation. And as a first step, we calculate corrections in a simplified model with heavy nucleon and relativistic lepton. This model correctly gives us leading logarithms, which I have just mentioned. I show the ratio of cross-section after radiative corrections to 3 level. On top of virtual corrections, we always account for soft photons, and in this plot, we include one soft photon with energy below 20 MeV. This result is given by solid line. We add on top the radiation of real photons and see a cancellation of virtual with real contributions. Motivated by experimental resolution, we take cone of size around 10 degrees for electron flavor, while for muons of smaller size. Corrections are the same for neutrino and antineutrino scattering. Adding radiation of non-collinear hard photons, basically all hard photons, correction becomes flavor independent and has a percent size. The other interesting feature is how leptons radiate. I show the leading contribution to radiation when energy of final lepton and photon is fixed. For electron flavor, radiation is peaked in the direction of electron, while for muon flavor, there are almost no very collinear photons, and radiation has slightly shifted peak with respect to the muon direction. That's why it doesn't make sense to consider collinear radiation for muon flavor. So far, I have described model-independent effects in the leading approximation, but we can do slightly better. And we formulate radiative corrections in factorization framework, since we have a nice separation of scale. As in many processes, cross-section is expressed as product of soft, collinear, and hard functions. Each function describes the corresponding integration region in virtual diagram of phase space of real radiation. In applications to low energy QED, soft and collinear functions are calculated analytically. We determine hard function at GeV scale when the ratio of scale over neutrino over mass of proton or neutrino energy is not large. There is one complication at this step. Our hard scale is of GeV energy when we have already mesons and baryons as effective degrees of freedom. That is why we use a simple model for the hard function. For virtual corrections, we consider exchange of virtual photons between charged lepton and nucleons. We use free nucleon propagators and assume on-shell form for each vertex. To correctly reproduce infrared behavior, we add self-energies of all external charged particles. To correctly reproduce also collinear limit, we modify electroweak vertex in a suitable way. We perform a renormalization group evolution of hard function from hard scale to low energy scale and calculate cross-sections at low scale, accounting for large perturbative logarithms by this. Before presenting the results, I would like to mention which errors we include. At 3 level, we take the most recent parameterizations of nucleon form factors from the experimental data, which allow rigorous error propagation to our theoretical predictions. Loop diagrams are calculated with dipole form factors, and we vary the dipole parameter by 10%. To account for off-shell effects and inelastic intermediate states, we assign the contribution when photon couples to neutron as additional error source and adding quadrature symmetric contribution when we vary proton form factors by neutron form factors. These plots are for the fixed neutrino energy and soft photon cutoff, and the momentum transfer is shown on x-axis. On the level of ratio of cross-section to the tree-level result, leading error from tree-level form factor cancels, and we have uncertainties at a few per mil range. Looks good. Let us switch to results now. On these plots, I present again the ratio to tree level for neutrino-neutron and antineutrino proton scattering in case of electron flavor. Observable with soft photons only below 10 MeV is shown by dash-dotted lines and relatively thin band. It is compared to observable including collinear photons as well. The radiation comes mostly from collinear region, and since the real radiation always increases cross-section, the cancellation with virtual corrections is pretty sizable. At tree level, the ratio is 1, while uncertainties of tree level are presented by green dashed line as a deviation from unity. For muons, the uncertainties are almost the same, but the correction is much smaller itself due to smaller scale separation between the muon mass and neutrino energy. In oscillation experiments, we are interested in electron over muon flavor ratio, which I show on these plots. Leading order result is very close to 1. On the level of exclusive observable with collinear photons for electrons and no photons for muons, the ratio changes up to a few percent at 2 GeV neutrino beam. Small error represents the cancellation of hard function between electrons and muons. Let us switch to other type of corrections, which include all hard photons. In this case, for inclusive observables, there are different ways to determine kinematics. The momentum transfer can be determined as the difference of neutrino energy and the energy of lepton only, or in more realistic case, we use here lepton energy, and if there is a photon within 10 degrees to the lepton direction, we, in case of electron flavor, we take the sum of lepton and photon energy. For illustration, we also provide the observable when Q square is determined from the nucleon lag, which corresponds to lepton plus photon energy for any kind of radiated photons. We see here that the radiation of real photons becomes relatively uncertain going to larger momentum transfer when event rates decrease. Also, we see a significant dependence on the kinematical reconstruction in the experiment. For muon flavor, this dependence on kinematics is still present, but corrections are slightly smaller. And finally, I present electron over muon ratio. As it is expected, the energy in cone observable, which is our closest relation to modern experiments, is quite close to EL plus E gamma spectrum and is very close to unity. This ratio shows a significant dependence on the details of reconstruction of kinematics. Our results for this ratio can be useful in predictions of electron-neutrino cross-sections based on measurements of muon neutrino cross-sections at near detectors. To conclude, exploiting factorization framework, we have formulated radiative corrections and evaluated charge current elastic scattering, cross-sections on nucleons, and various cross-section ratios. We have illustrated that corrections depend significantly on the way to reconstruct kinematics, and have provided simplest process which illustrates that even without percent level knowledge of cross-sections itself, we can relate muon cross-sections and electron flavor cross-sections with sub-percent precision. I'm grateful for sharing my research at this workshop and will be happy to answer your questions.